Jæja, verið sæl komið sæl og verið hjartalega velkomin í Veröld hús Vigdísar. Ég heiti Jón Emil Guðmundsson og kennari í eðlisfræði í Háskóla Íslands. Ég ætla að hoppa yfir á ensku eftir nokkrar setningar, en áður en ég geri það þá langar mér bara til að segja að þetta er þriðji fyrirlesturinn í fyrirlestarröð stjarnvísindi á þessari önn sem skipulagður af Stjörnuskoðunarfélagi Seltjarnarness, Staðvísindafélagi Íslands og Háskóla Íslands. Og við hjá félögunum erum mjög þakklátt fyrir það að Háskóla Íslands skjóti yfir okkur skjólshúsi og geri þessa fyrirlestarröð mögulega. Og fyrst þegar ég með athygli þá ætla ég að benda á að núna eftir jól þá kemur Sigríður Kristjánsdóttir sem er einmitt formaður Stjörnuskoðunarfélags Seltjarnarness og hún ætlar að fjalla stelpur í stjörnufræði. Þannig endilega merkið þessa dagsetningu í dagatali. Okay, now I'm going to switch to English. So first and foremost, Jeff, welcome to Iceland. I hope you enjoyed the Northern Lights that we put on show for you. Many of you, well, you haven't read Jeff's CV, but what I can say before, and we don't actually know specifically what Jeff is going to tell us about from curiosity to the cosmos. But as a colleague of Jeff's, I can say that he has made critical contributions to some of the most advanced telescopes in the world. These include the South Pole Telescope and the Atacama Cosmology Telescope. And I'm sure he can tell you lots of interesting stories about what it's like to design an instrument, build it, and then see it produce state-of-the-art science. He did his undergraduate at Berkeley, PhD at Princeton University, postdoc University of Chicago, then to Michigan, and then back to Chicago, and then finally you're in Iceland. So perfect. Take it away. Thank you so much for being with us.
Oh, thanks so much for the great Yeah, thanks for the wonderful introduction. So, I was thinking about what to do for a public talk, and I thought that what would be fun for me. And when I was a kid, I lived in the Netherlands, and there was this book that I walked by in the bookstore when I was about 5 that had a space shuttle on it, and I just had to have it. My mom's like, I don't think that's age appropriate. And so I begged her for what seemed like forever. It was probably like a day and a half, and I finally got the book. And I looked at the pictures inside of it so much that my brother has them all memorized. And it was pictures of astronomy as it was known in the late 70s. And they were beautiful. I was kind of thinking, I'll start this talk by showing you images from that because they're just so captivating. But I looked at them, and over the last, 40 years, 50 years, we've made such incredible progress that I could show them, but they would be a disappointment. And that makes me incredibly happy, right? Because the thing is, when you look at the astronomical images, they always blow you away. And the ones that we have today that were only possible, this is JWST, the James Webb Space Telescope, that only came online a few years ago. Can we turn the lights down a little bit? I think darker is probably better for this because they're really pretty. But you look at it, and does everyone recognize what that is? Yeah, it's a galaxy, right? And we know that, but they're just beautiful in an artistic sense, just of all the luminous light and all the things that are dancing. But they also tell this incredible story of how the universe works if you're curious and follow that curiosity. And so I just wanted to show a few pictures to sort of motivate us about what it is to be an astronomer. Because I think it's pretty easy for people to think that we just take pictures. And we do. But there's more than that. You look at them and you just think, what is that? And, I think that there's this perception that science is hard to be part of, that you have to be special or, these magic people go do it. But it's not. It's just people who take pictures, who really perfect their art of taking pictures, and then think critically about what they're seeing. And so, these ones that I select them not just because they're beautiful, but they also tell a story, right? This is a galaxy. We now know that. We take it for granted. Later I'll ask you how long we've known that, but it's not as long as you think, right? Like, do people know how long we've known we lived in a spiral galaxy? What did it say? No, it was in the 60s. The late 60s that people figured that out. It's really hard to figure out where you are. So there's all these things that we just think are obvious facts that every child knows because we disseminate them so fast. Once you realize how these things work, it's just magic and everyone just takes them for granted, but they're really hard-fought victories. And I want to celebrate a little bit of those victories. This is, the pillars of creation, one of the most beautiful sort of star-forming regions, but this tells the story of how stars form. We know that. These are two galaxies that are colliding. It's easy to think of the universe as this static place that goes on forever because, in the blink of our lifetimes, it does. But galaxies are these dynamic things that wouldn't work if they weren't always moving and always kinetic. And then there's this, which is the Hubble Deep Field, where people pointed to an empty spot of sky just to see what would happen. It was a project that was dreamed up by postdocs, and the director of Space Telescope Space Institute said, sure, go for it, whatever, that could be fun. And it's turned out to be one of the most transformative things because everything you see when you look harder is just amazing, and this shows galaxies back almost as far as you can go, right? And they're just beautiful. So those are motivational. But the questions I really want to ask today are like, how did we get here? And there's a lot of room in that question. It's a good one to come back to when you're looking for something to fill the time. But how do we get here in a couple ways? One, how did we actually get to the point where we can just make images like that, take them for granted? How did we get here in the sense of understanding the universe? Because we have this beautiful model where now people believe that the universe is expanding, that time had a beginning. People even think that extensions to that, like the multiverse, may be common, and if you watch a Marvel movie, it has to come up. And it's how did this proliferate? How did it all happen? And also, what is it that took to build it? And so I want to sort of start back about 100 years ago. 100 years ago seemed like a convenient amount of time because it seems like forever. But it also doesn't seem like it's completely barbaric. Like they weren't cavemen, as far as I know. And it's sort of fun to look at it because this is Chicago where I live. And if you look in the middle, you'll see that there are tall buildings. They had elevators. You could just ride to the top in style without, walking upstairs. Big advance. We had electric trains that you could catch or miss. But transportation was revolutionized. If you go to the beach, it looked a lot the same as it does today, except now people don't wear suits. They wear bathing suits. I actually have that hat, but I didn't dress as well when I went to that park. There's the beach, there's Lakeshore Drive. Everything was really modern. We even had social progress where women could take a car out and drive, which probably was actually a little bit revolutionary back then, right? So the world was really moving forward, and it must have seemed like a really amazing place where anything's possible. And that's sort of the world where a lot of the advances, and I think really the history of big telescopes, big glass, big science astronomy started. And I'm going to introduce this one guy, George Ellery Hale, who's not well known, who was an astronomer who discovered magnetic fields in the sun. But really his claim to fame is that he had nearly a century of the biggest telescopes in the world that were productive. There's a little bit of an asterisk in the from the 70s on, but I'm going to give it to him because there was technically a bigger telescope, but it didn't really work. So I'm going to give the credit to him. And so that's pretty amazing, right? Like a century of the biggest telescopes is owed to this person who grew up in Hyde Park, which is, or not Hyde Park, but the Kenwood, the nicer neighborhood north of it in Chicago. And his dad actually made a bunch of money with those elevators. And so he just got fascinated in high school by astronomy, and he went off to MIT, came back, and at 22, his dad let him build an observatory in the backyard. This would be about 1.5 miles from my house, but sadly it's not there. I would go by there every time I could. But it looks like it's a really nice addition, right? It's something that maybe you could imagine even doing in your house or someone in your someone could do it around here, right? It's not that big of a thing. It's just a structure like your house, and it had a 12-inch telescope in it. But at the time, that was not a bad telescope, and he managed to actually make some spectral measurements of the sun really well from it. He founded the Astrophysics Journal, which is still one of the premier journals of astronomy, and he was 22, right? I just can't believe that's the part that blows my mind. But of course, that wasn't big enough, and what he really wanted to do is build the biggest telescope in the world. And so the guy who built the elevated trains, the L trains, but I put a little elevated in there to help you because no one knows why we name our trains after the letter L in Chicago. and the London Underground. But when he built the elevated trains in Chicago, he dug up the road so bad that everyone just hated him. They thought he was a ruthless businessman, and they also wanted to be able to walk and drive, and they couldn't because he was building the elevated trains. So he had a bunch of money, and maybe he wanted to like rebrand himself, or maybe he was just generally interested, but he actually gave the money to build the world's largest observatory. And this is a little bit before 1920s, but this is the Yerkes, basically a 1 meter refractor that was shown in the World's Fair in, I think, 1893. And this thing, was the world's largest telescope, and it was one of the major attractions where people would just line up to go be able to go see it. And, it's pretty impressive. It's an incredible monument of science at the time, still is. In fact, you can go see it in Wisconsin. But the fun thing is that, the way these things are made, and this, as Jan said, I'm deeply an experimentalist where I build all sorts of things for telescopes. They're still made the same way, where all these like precision parts, you have people that go out there and just lovingly polish the glass until it's the right shape or do whatever it takes to do it. Now, these people were admittedly dressed better than we are today, but still morally equivalent. And it just makes me sort of happy to see that there's this long legacy that you come up with this big plan. It's very expensive. You have to do all this stuff. But at the end of the day, you just have to figure out how to do it. And so this is what the output of that was, which is the Yerkes Observatory. And the thing I want to point out, why I'm bothering to show this, is there are 3 domes. So the largest telescope in the world at the time was over to the right. But then there were all these buildings. And the thing that I think makes this one of the sort of birthplaces of modern astronomy is that they had the foresight to build these buildings there where they had labs to do atomic physics so you could understand what the starlight meant. They had labs that you could understand how film worked so you could really understand what your images worked. It really was like a multidisciplinary center to really start attempting to make astronomy from just taking pictures into more of a precision science. It's not the only place that was happening, but it was really one of the centers of it. Now, of course, the bad part is that it was in Wisconsin. It's convenient. It's only about an hour and a half from Chicago, but the weather's not good. It's like doing astronomy from Iceland. You have to wait for the good weather. Although today was really great. All right, but so you got pictures like this that came out of it. And I just want you to think back. I showed you the pictures of all the people in the 1920s. This would be shown, circulated in magazines. This is actually a reprint that came out of a book. But think about what it would be like to see that for the first time and think, wow, that's amazing, right? We have that image when we're seeing the James Webb, like the feeling we have, but people would have felt the same way. And at the time, we all know that's a galaxy, but at the time people had no idea. They just thought it was a swirling cool thing. They probably said it in a slightly more refined language, but it could just be a ball of gas in our galaxy. They couldn't tell how far away it is, so they had no idea how big the universe was. And, answering that question is really, really non-trivial because measuring things that are far away is hard, right? We do this with parallax in our eyes, where if you just blink left and right, you can see things move a little bit and your brain puts that together. But once stuff's, 100 meters away, it doesn't work that well, right? You just have to, your brain builds a different model. And for things that are as far as stars, that'll never work. And so it's very, very tough to find out how far away stuff is. So at the time, people were probably captivated by this image, but they were asking, what is this thing? How far away is it? How do we understand it? So the question is, how do you answer these? Like, how do you find out? And what's neat is that, it kind of falls into sort of 3 categories. It's not just one thing, but I think one of the most important ones is you need to build new and better telescopes, right? And, why do you build new and better telescopes? It's because of curiosity. You want to know what you can see, and you want to answer questions you couldn't quite do before. But I also love this picture where, this guy has built this thing that is still a world-class mirror. Like, this is a beautiful mirror. I have no idea how they polished them by hand in a kind of wood shop, right? So this was the 60-inch mirror that went into the Hooker 60-inch telescope, which was the largest telescope after Yerkes in Mount Wilson, which is a very good site in LA, aside from the lights of LA, which have ruined it. And this is actually the trail that's about 2 miles from my house that goes up to where I grew up, that goes up to Mount Wilson. And it's just fun to see that, like, 100 years ago, just over 100 years ago, people were using donkey carts to move precision machinery. We have trails in Chile where we build our telescopes, but you use semi-trucks now. But so it's changed a little bit. I'm going to fast forward over that one and just go to this, which is the one that came in 1979 or 1917, which is the third telescope in 30 years that was built that was the world's largest. And this one was really, really transformative. So this is where we're going to sort of dwell on a little bit. But besides that, you also need to think about techniques. And in astronomy, we don't just look at pictures, we don't just make images, we also have to figure out how to interpret them. And distance is tough, but there's a great way to understand how to measure distance, which is by just looking at how much light you get from something, right? If you have a headlamp and you're about 100 meters from someone, it's no problem. But if your brother or sister comes over with a headlamp and just like points it right in your eye at like a couple inches, it really hurts. And that's the principle of like luminosity distance. You can kind of see here with these street lights, the one that's really close is giving you a lot of light, the one that's farther away gives you less. And so if you can just measure the amount of light you get, then you can learn how far away things are. So that's great. But with street lights, you kind of have a good idea that they're all the same. They probably came from the same factory. They may have come from the same factory on the same day. You know that they're not going to ship them if they're terrible. So you know that these things should be the same intrinsic luminosity, but you have no idea when it comes to starlight what's what. And that's where this woman, Henrietta Swan Leavitt, who was an astronomer at Harvard around the turn of the century, which is a story in its own right there's a lot you could say about that. But she did absolutely brilliant work, and she discovered by just being painstakingly poring over glass plates and measuring the brightness of fluctuating stars, that there's a type of star called a Cepheid that basically just has an atmosphere that heats up and expands, cools off and collapses, and sort of goes through these cycles that are very predictable. It's just sort of like a pulsating star. And the thing that she showed was that the pulsation period was deeply related to the intrinsic luminosity. So if you just measure how fast it's pulsating, all of a sudden you know the wattage. And that, in and of itself is really cool, but the place that that's really cool for is that all of a sudden you can now do luminosity distance. And so this new sort of observational tool of characterizing stars all of a sudden turns into this ability to measure distances in the universe. All you have to do is find them. And so fast forward a few years, and Hubble is making images at the Mount Wilson 100-inch. And right now, when you think of taking an image, you basically point a telescope at something, you let the computer do your business. It has a servo system, it tracks, everything works, it's marvelous. Back then, there was no such thing, and so the observer had to sit in a cane chair. I don't know, it just happened to be cane chair. It's still there, by the way. And when I was there around 2000, I got to sit in it, and I was really happy about that. You would basically just sit there with these wheels and slowly, watch one bright star on a crosshairs in a reticle and adjust to make sure that it stayed centered. And you'd have to do that all night. And, Hubble, there's lots of stories about Hubble where he would fake a British accent and do other stuff that was a little bit pretentious. But at the end of the day, he was a very good astronomer who could just, had the focus to sit there and make some of the best images. And one example is the so-called Var plate, where, you see this little N where he thought he had found a nova, because he just was looking at this plate compared to other plates. And then all of a sudden, it dawned on him that no, it was a variable star. So he was looking at a galaxy, but he found a variable star. And so immediately you can then get a distance from it. And the thing that was surprising is that people had thought that these things, which were just called nebula at the time, were in our galaxy. People didn't know that there was really, they thought our universe was the whole galaxy. And so instantly our whole image of how cosmology fit together changed, right? We knew the universe was vastly bigger than we'd expected, and that they were now filled with galaxies and we weren't alone. It's pretty cool. But it also meant that now, anytime you can do something once, you can do it a bunch of times. And, the sort of measurement you make that's transformative one day turns into the tool for making the next measurement. And that's especially true in this one, because all of a sudden he could measure, the 20 or so nearest galaxies. And I've told you about distance, which is the x-axis, and it's in parsecs because we're annoying astronomers. But it's just distance. And the other one is velocity, which is very, very easy to measure because it's just the Doppler shift, right? So if you hear a siren, ambulance go by you slowly, there's a little shift. If it goes really fast, there's a very big shift, and it's fun to listen to. It's the exact same thing with light. And so there's this miraculous thing that happens, which is the farther away stuff is, the faster it's going away from you. This is the Hubble expansion. You've probably heard of it or seen it maybe before in one of these lectures, but it basically shows that the universe is expanding. Now you may say, well, how do I think about this? It's, we'll come back to that in a slide, but basically the other ingredient besides just, great observations is you also need a theory. And so, this is at around the same time general relativity had come out. And what general relativity does is it's a theory of gravity. And it's a modern theory of gravity where you don't just have mass and instantaneous action like Newton's laws, but instead you have this dynamics where mass or energies interact with the fabric of space-time, with space, and space becomes a dynamical quantity. So distances in space can stretch. And so space is now a thing. It's really fun. I also like that Einstein, people think of him as this genius who just, did his genius stuff, and of course he did. But he also just hung out with his wife and went sailing. It's nice to think of these people as relatable. But because of this theory of general relativity, there was a ready-made theory to explain what went on, where basically this equation has two parts. It has a left side and a right side. On the right side, there's the stuff in the universe. Yes. On the left side, there's space-time. And so basically, the stuff in the universe tells space-time how to move. And then there's this other funny thing, lambda times some funny symbol, g's and mu's and nu's, which is a cosmological constant that Einstein originally put in there to make sure the universe would be static because he knew it had to be static. And this is the thing he called his biggest blunder. Of course, we know the universe, is interesting, and maybe there is a lambda, but let's forget about that for now. But there was this ready-made theory, and people could understand what they were seeing. And so, to recap, basically, by 1929, we had measurements, both the images of galaxies taken over time, so you could actually see the varying stars, and the calibrated Cepheids so that you could interpret them, and a model based on general relativity that showed we lived in an expanding universe. And I think I've just shown this balloon diagram up there to sort of help out with that because, one of the great things is that the way this works mathematically is that you have two things, galaxies that are near each other, and then their distance is just the distance in some coordinates times this factor which can change, which is how space is growing over time, and you don't need to be expanding into anything. That's sort of hard to visualize sometimes, and so people want space to be expanding into something. So there's this 2D analogy where if you just put dots on a balloon, it's probably better if they were in a straight line, and then you blow up the balloon a little bit, everything gets farther apart. And so you can go from any one of those galaxies and they'll see the same velocity. So everything looks like it's spreading out, so there's no center. And if you look carefully, something that's very close has very little space, so its velocity is low, whereas the more space you have between things, the greater the space, and that's exactly what Hubble's law said. So, by 1929, we had this beautiful model of an expanding universe, and it's thoroughly modern. So the question is, did we have it all worked out? Well, the thing about curiosity is that you start by just understanding what a galaxy is. Then all of a sudden you've found that you've discovered the expansion of the universe. And I think that's what I love about curiosity-driven science, is that the thing you start doing leads to another thing, and you get surprises. If we knew everything that we wanted to discover and made a list of it, life would be really boring. What's fun is the universe will throw you a curveball if you just keep trying to understand and chip away at it. And so this discovered, if you look just at what happened historically, this really heightened curiosity, because now the question is, how do we confirm this model? I mean, this sounds a little crazy. Space is expanding. So you have to look for other ways to measure it. Anything worth measuring twice. well, if space is expanding that had a beginning, how did it begin exactly? But then if it's still expanding, what's its fate going to be? What's going to happen in the end? All of a sudden, these questions, which are existential and philosophical, became scientific, and that's pretty magic. And then, how has the universe evolved over time? And so working on all those has been this great, beautiful piece of progress. But going back to, around the, at least before the 90s when we knew the answer, there was this big question of how the universe began. So, it was Big Bang, but there's different spatial curvatures that can lead to different future histories. So it could be that the universe has enough matter in it so that it just recollapses, in which case we'll end in a big crunch. It could be unbound, in which case everything just flies apart and you lose all your neighbors and you can't see any other galaxies beyond our own and life is pretty boring. Or it could have just been, this thing where you throw a baseball up and it, instead of falling down to the earth or flying away to infinity, just sort of hovers with zero velocity really, really far away, right? This sort of magical case. People didn't know it, but there was this big quest to understand this, and the way they wanted to do it was by measuring the deceleration parameter, right? So we believed we lived in a bound universe, and if we knew how fast the acceleration of the universe was slowing down, then we would know, we could be able to confirm that. And so in the 90s, I'm kind of fast forwarding over some stuff right now. There's other questions we'll come back to too. Oh yeah, there's one point I should make here before we move on, which is that if you run time backwards, the distance between stuff gets really small, so it's like compressing the entire universe. And what happens, if you compress something? Yeah, it gets really hot, right? So the universe gets arbitrarily hot, and since the distance should go to zero in this model, it could be hotter than anything. And so the question is, can you see that? That's a really fun part of current research too. So anyway, I think people, in the 90s, two groups went out and used the Hubble telescope to measure the acceleration of the Hubble constant, or deceleration. And the deceleration came out that they measured it, but it was negative. And that's, how does that work, right? So, okay, this is all gravity, right? So we can actually reason with like what we know about gravity from just like jumping, which is if you throw a baseball up, it usually comes back down. So that's like a deceleration parameter that's positive, right? It's coming back down. Even if you threw it past the escape velocity, it would slow down as it was leaving. So if you see something that it has a negative, is accelerating away from you, and you have a model with gravity, you know something's broken, or you know someone's messing with you, right? Someone's put a rocket or a string or something on the baseball and is tugging it away from you. And this accelerated expansion means there's an extra force of nature, and that's what dark energy is, right? And so basically, you start with this, the sort of restarting, I would say, of once you discover the universe is expanding is you want to know the details. You want to know exactly which, you're curious for what model you live in. And the funny thing is that we actually live in a model that no one expected that's not even on the map. And I find that really, I was an undergrad at Berkeley when this was discovered, and it was electric just knowing that we were surprised, knowing that like our curiosity had led us to something that asks more questions. And one of the things that's very odd about this is that we have this beautiful standard model of particle physics, and that only describes about, under 5% of the stuff in the universe. And this is more like 70. So we have no idea what 70% of the energy of the universe is. And then there's dark matter too, which I'm not going to get into today. So the other question is what happens early on? And there was this great confirmation that started in the 60s, sorry, the text is off the bottom, and then culminated in the 90s, where we measured that the temperature of the sky in every direction is 2.7 Kelvin. And why is it that? Well, it turns out that the universe was so hot early on that everything was ionized. So if you were there in the universe about 380,000 years after the Big Bang, everywhere would be like the surface of the sun. You'd be several thousand degrees. So that would be a bad place to live. So life didn't exist back then. But the neat thing is that as the universe expands, that light just goes through the universe and gets stretched out by about a factor of 1,000. And so that light is everywhere. If you look up and you had millimeter wave eyes, you'd be able to see it in any direction. And this is exactly what you'd predict from a Big Bang. And so this is the second of the three pillars of the Big Bang. So it really, really, helps with that. Now, of course, whenever you see something that someone says is constant, you ask, is it really constant? Right? What's actually going on here? And if you actually zoom in on it, you can see hot and cold spots in the cosmic microwave background that have a contrast of about, a few parts in a million. So it's really small. And you've probably seen these before. And to me, these look really exciting. Maybe it's because I went to Berkeley and it reminds me of tie-dye. Maybe it's because I'm an astronomer and I know exactly what they are. But how do you actually understand these? Well, I think there's this beautiful analogy, which is this. So what can you tell that happened in this picture? Or before this picture? Did someone shoot it? Yeah, why does it sound? Yeah. If it was a bullet, you'd see everything going in one direction, and it's radiating out, so you can tell it's a sound wave. The other thing is, from this, you see the shards have kind of a characteristic length, and you can tell something about the wavelength of the sound, right? So you look at a picture of destruction, and it actually gives you huge handles on what destroyed it. And so when you look back at the cosmic microwave background, you're being given this sort of sound waves of the early universe. There's no shards of glass because it was smoother. It wasn't like a medium that could fracture, but it's the same idea. And so these hot and cold spots are actually the imprint of what happened in the first maybe 10 to the minus 30 of a second. And since we've started being able to measure these things, we can actually infer what happened near the beginning. And I find that to be, this is now getting into active research, but because of all this work that we've built up over the last, I think really over the last 30 years is when this has emerged. We now have this unbelievably beautiful model of cosmology that can be encoded in a cartoon that looks like this, where we start off on the left side and time is logarithmic. So this is the beginning of time. And you may be talking, right off the page is stuff that had to happen that may have happened at 10 to the minus 32 of a second. Does everyone have an intuitive sense of 10 to the minus 32 of a second? Yeah, I don't either. Well, let me help you with this one, though. Okay, so the smallest object that has size is a proton, because it's made of quark, so it actually has a physical size. It's not point particles. It would take light a trillionth of a second to cross it. 10 to the minus 32 seconds is a trillionth the time it would take light to cross that. So it's just unbelievably a small time. It's also unbelievably high energy. And what's crazy is that we actually have a model of the physics at that time and that energy scale, which is about 1 trillion times higher than the Large Hadron Collider can ever reach, that tells us how to predict the types of fluctuations we see in the cosmic microwave background. It's not a unique model, it's a family of models, but we're starting to actually understand the physics of that early universe, and this is called inflation. Of course, we also know the sort of contents of the universe, dark matter, dark energy, stars, but that allows us to also build a model of how this evolved, because you start out with everything being very, very smooth, but those hot and cold spots correspond to where there's more density, and under gravity, anywhere that's more dense starts sucking stuff in and growing structures, so over time you grow the galaxies, galaxy clusters, us, all that stuff. And sort of a fun way to look at this is that we wouldn't form without quantum fluctuations in the early universe. Like none of us would be here. We owe our existence to like quantum mechanics at this insane energy scale. I think it's really amazing. Now, of course, this model, one question you might ask is what exactly is inflation? What is dark energy? What is dark matter? And I think that's what's great about science is that, we answer some questions, then we find new ones. And at some point we may be done, but we're really not close to that right now. So there's so much to do and so many potential new discoveries. It makes me really excited. Now, the other thing I was thinking of in this is I want to know the history of big science a little bit. And it sort of touched on that with the beginnings of it. And I was trying to understand, like, where are we going now? Like, I was trying to reassure myself, right? Whenever you want to understand the future, look at the history. And you can see what I'm doing here, right? Leavitt's law, general relativity. General relativity came right in the middle of World War I. The Mount Wilson 100-inch was during World War I. The Hubble expansion was right before the Great Depression, so that was probably a great time to be doing science. Dark matter was in the Depression, the first detection of dark matter. World War II saw huge advances in nuclear and particle physics that may be correlated. So sometimes, like, politics steer science. But then we've had this tremendous progress since then. And so, including, accumulating evidence for the physics of the very early universe over the last 20 years. And so I take a lot of solace in this, that, the scientific enterprise and human curiosity is really robust and will kind of continue us forward, hopefully no matter what happens. I'm American, you can tell what I'm thinking here. So that's sort of one of the things that was here. The other one is I just want to bask in how much progress we've made, because I think it's easy to take it for granted. So, this is the Vera C. Rubin. I started by JWST, which came on, 5 years ago, something like that. But there's new telescopes going online, like right now, that are also just incredibly transformative. So this is the Vera C. Rubin Observatory, which has the largest camera that humanity's ever made, to my knowledge, of 3.2 billion, 3.2 gigapixels. And it can image the whole sky in a couple days, and these are just, deep, beautiful images that are amazing to stare at. In my field, we got rid of the state-of-the-art observatory that published its last results in the last few months, and replaced it with an observatory that can do the same thing it could do in a tenth the time. Or put another way, in the same amount of time, we'll do at least 10 times more. And this is the telescope I work on. It's at like 17,000 feet, which is 5,200 meters. In Chile, it's a beautiful place to work. There's actually not just one telescope, there's 3 here, and there will be 7 in the next 2 years. But it's going to revolutionize what we can do. In fact, we're already starting to get data from it. And hopefully from staring at those maps of tie-dyes, you'll appreciate my pride in these images, right? I mean, just when you turn on a telescope and you get these sort of beautiful things happening, it's all really reassuring and really, really exciting. And then finally, there's extremely large telescopes. I should have shown the European extremely large telescope here, which of course will be even bigger than the ones that we planned in the US. But that makes me really happy that, we started with a book about a space shuttle, and now we're building telescopes that are much, much bigger than a space shuttle. And, at optical, this is just insane. We're going to be able to see all sorts of things in the early universe, maybe get spectroscopy on extrasolar planets and many other topics. So, over the past 100 years, 100 years ago, the way you got a telescope funded was you asked a rich person for it. We had a period where you ask your government for it. I think we may be transitioning back to the other one. My own research is that way. And, I have qualms about that, but I think the point is that people still are inspired by the science and want it to happen. And so I'm kind of less worried about that, because there's always been a shift in the model, and we've always moved science forward because people see the value in it. I think that the thing I hope I impressed on you is that if you just look at a beautiful image and ask what's going on in it, and stare at it long enough till you start figuring out how to make progress on it, that's what being a scientist is, and it's a blast. And I just hope that we keep, as a society, fostering that curiosity in everyone, where if you see a thing like that, you appreciate its beauty and want to know more and want to communicate it. The other thing I hope I impressed upon you is that the rate of progress is incredible in astronomy, where things that are state-of-the-art 1 year, in 5 years may look terrible. And that's the one that makes me so happy. I work really hard to make these images good, and then it's really happy when I make them look really bad by making them even better in the future. And so what I look forward to is that our new telescopes could answer some of the questions that are ongoing about the nature of dark matter, dark energy. give us new surprises. But right now we are absolutely at the high water mark of human knowledge of astronomy, cosmology, and science. It's just amazing to be here right now as a person and know all the things that we get to know and that we can ask about. But we're not at the pinnacle of human achievement. We're still moving towards that and may never get there, which is kind of fun. So I feel I sort of wrote this talk to make me feel optimistic when I was worried about like funding and other things. And I just sort of see all the stuff that's happening that's good, and it really cheered me up. So thanks. Great. Yeah, okay, good. All right, this gets into like slightly nerdy math. Basically, once you generalize, the geometry that you need to describe general relativity actually has a spatial curvature to it. So what is curvature? Well, we all have maps that are flat, but we know the Earth is a globe. And so the Earth is an example of a curved space, right? The surface of the Earth, you can walk along the equator, walk to the North Pole having turned 90 degrees, turn 90 degrees, and walk down to the equator. So you can actually have a 90-90-90 triangle. The angles don't add up to 180, right? It's 90 too high. On a plane, that could never happen. And so the sort of, the nature of triangles is different in open, closed, and flat spaces. And the closed one that's like a sphere is very easy to explain. The open one's funny with a saddle. But the basic idea is that space can have a structure to it that creates curvature, and then that curvature will actually drive what happens with the future of the universe. In those examples, the one that if the universe were closed, which would have like the spatial curvature, like the triangles would add to more than 180, it would recollapse. If it were open, it would expand on forever. And so there was this 100-year quest, which I didn't do justice to at all once people knew we were in an expanding universe, to find out which of those cases it was. And we figured that out in the late 90s with the measurement of the CMB, where we found out that the sort of shards of glass were a certain size. And by knowing that, you can basically do this trigonometry to figure out what universe we're in. But right before that, we'd found out that we have dark energy, so accelerated expansion. So we now know the universe is flat, but it's also going to have a future where it gets really spread out. Which I used to be sad about. Now I'm not sad about it. I don't know why. Oh, I'm going to blame AI on that, but it's probably actually human intelligence. So. Yeah, I know. The thing, I really, I always ask myself, what is it exactly that I do as a scientist? And I think part of what I do, one of the views of that I aspire to is that I want to inspire people that you can tackle a hard problem and know the answer. And I think that there's a bit of being a scientist where we want to we hold ourselves to a high standard where if there's something that's wrong in the scientific literature, we will fix it. And there's an example where there was a detection of gravitational waves from the early universe that would have been amazing. We were all happy about it. People looked really carefully at it. We understood what was wrong, and now we're moving forward. And I think that rigor is really helpful. But why don't we have that rigor in politics and human history? It's harder. I think it's really like getting humans to do this. People always talk about cat herding. Do you guys talk about cat herding? Yeah. Anytime you have, it would be great if our politics were one steady piece of progress. But yeah, that's something I don't understand. I hope you understand it. Yeah. 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 Dark means we know there's a thing and we don't know what it is. Now, I think there's this, perception that physicists just make stuff up when you hear about dark energy, dark matter. And the thing about those is that we don't introduce a new thing into our models unless we have to. We hate doing it. I mean, we're thrilled when we get to, but like we have a lot of skepticism and rigor to allow that to happen. And so the easiest way to see it is with galaxies. They rotate. If they didn't rotate, they collapse, right? So a spiral galaxy will rotate. This isn't the way the original detection was made, but Vera Rubin did this in the 70s, and that's when people really believed it. But basically, if you look at them, you can measure how fast the stars are going. So you can see they're going at some speed. These ones go towards you. These ones go away if it's edge-on spiral. And you can then make a model for where the mass would be if the stars were all the mass. And what you find is that the stars wouldn't be on a stable orbit at the speeds they're at. They would be, escaping or doing funny things. And so immediately when you look at that, you say, okay, I built a model with all the physics we know, gravity, and it won't hold the thing together. There's got to be something that's holding it together. And so it could be dark matter. It could be that our theory of gravity is wrong. But if our theory of gravity is wrong, that's a really challenging question. So we think the right thing to do is to add this dark component of extra mass. But everything can be understood with baseballs, right? I mean, or soccer balls, footballs, sorry. I should know that, right? So if you kick a football up, if you know how much, matter there is around you, you should be able to predict how fast it'll come down or what'll happen to it. And the answer is when you do that on a galactic scale, you find out that there's much more stuff there. And so we think it's some type of matter that's dark. We don't know what it is. And yeah. Yeah, so we know a lot about its spread. Actually, every galaxy lives in a halo of dark matter. There's predictions of subhalos. We're starting to really push down to smaller scales, but it's not uniformly distributed. You couldn't form galaxies without it. And so, yeah, now the question is, what is it? People have come up with endless lists of funny names. Machos. Oh, it could be... Yeah, it always could be. I think the starting point is let's come up with lists of things it could be, and then see if any one of them works. And then it could be that it's multiple things. I mean, the world can be very complicated, but I think right now people are trying to look for a single thing. So people have looked for like mini black holes, and then they did these ingenious measurements where they looked for microlensing. So if there's a bunch of black holes floating around the galaxy, you should be able to see stars get deflected by them as they pass in front of them, and that is ruled out. People have looked for WIMPs. There was like a theme in the 90s when people were coming up with all these models, which are weakly interacting massive particles, which are particles that couple to the standard model of particle physics, but not to light. And so far, those haven't been found. They've started pushing down to levels where it's starting to get uncomfortable. Now people are coming up with things called axions, which are named after a laundry detergent, because it was a way to clean up this problem in a model. And actually, I was just at UT Austin where, what's his name? Not Wilczek. Weinberg, yeah. Stephen Weinberg who came up with these, and he has a bottle of like a little box of the Axion detergent in his office that I got to see. He passed away, but I actually get to go in there. It was amazing. So people are trying everything they can to fit into the theoretical framework of physics, and then building huge detectors usually underground to look for these particles, but no one knows what dark matter is. And it could be something as crazy as maybe string theory is right. I mean, and then with 10 to the 500 different choices, anything could happen. But one of the things that could potentially happen is there's like another universe parallel to ours that's just different, that couples only with gravity. So it may be like some weird tug from a neighboring universe. There's all sorts of stuff. But I think the fun is trying to figure out what it is. Yeah. Yeah. I haven't seen anything recently, but I've definitely seen, so basically when you do this dark matter experiments, you have this acceptance region where you make two axes of things that come out of your detectors, and the wrong types of stuff, like things from electrons or neutrons or problems, things that aren't quite clean in your detector, show up in certain bands. So you make a box that you think is clean, and then you look for dark matter in there. And 15 years ago, this one experiment had two detections that were right on the edge of that box, and I think they didn't claim a detection, but I remember thinking, so my friend said, that's the budgeton. You detect that, we need more funding to continue your work. So I think, no, but this is no way plays down their efforts, or I don't want to sound at all like I'm saying they're doing anything sloppy, because they're doing brilliant hard work. But there's you always push your experiment as far as you'll go, and when you see sort of weak hints, you still need a lot more work to be able to be sure of what you're seeing. And I think the work is amazing. I mean, there was definitely one group in Italy that kept saying they were seeing a signal, and that's now been ruled out. So it's hard work, and the work continues. Yeah, when you have separate issues, you always think, I think there are some models that try to pull all those things together. There are other models that just tackle one of them. No one really knows the answer. In terms of what we know, we have the four basic forces. We have gravity, electromagnetism, the weak force, the strong force. Three of those are quantum mechanical. Gravity is not. And there's this inconsistency where they don't quite fit together, and that's something that people worry about a lot. If you could actually put those all together, it would be a theory of everything. People would love it. When you start getting to the energies that we think would happen at the beginning of the universe, the uncertainty in our theory is a real problem, right? Because we probably don't, every time you build a theory like Newton's laws, it's going to be right for everything that it's appropriate for. Then all of a sudden you find that it breaks down, so now you have quantum mechanics. Then you find it breaks down, then you have general relativity. And I started out as a math major, and I really wanted, I had this naive 19 or 20-year-old I can just make physics axiomatic. I'll just figure out what the axioms are, and then I'll be able to reason what happens in everything. And physics is not math. We don't actually start with axioms. We're an empirical science, so we actually go out and measure and try to build the best theory we have. And so the theories that we have are marvelous, but I don't think they're the last word. There's something we haven't figured out yet. And in terms of what makes progress, you have to build the instruments, you have to know how to interpret the data, but you also have to have a theoretical understanding. And I think you can make huge progress by making any one of those work better, right? So if someone goes and meditates in a peaceful sensory deprivation tank or whatever, and comes out and says, I figured it out, I know how to unite general relativity and quantum mechanics, and this is what it says about the early universe, that'll be a marvelous day. And it could happen. There are people working on it. The sensory deprivation tank, I don't know why I thought of that. I just always picture this ideal of Einstein as a guy who went and meditated in a peaceful like room and just like did stuff, but of course he just worked hard, right? I mean, you know, that's how it always works. But that would help a lot. But then at the same time, maybe we'll be able to see a hint of, you know, let's say we, you know, a few years later, we manage to work hard and we see, you know, both, you know, Bicep Keck and Simon Observatory see gravitational waves, and we know that there's this new energy scale of physics. That may focus the mind and actually get that theory. But I think we're looking for breakthroughs at that level, both in theory and measurement, to be able to really understand that. What I'm amazed about is that in the 80s, maybe 70s, people talked about the first 3 minutes, because people had worked out how all the nucleosynthesis worked, how the hydrogen, helium, lithium had formed in the early universe, the exact ratios, they could predict all of that, and that was known. And you know, getting from like seconds to minutes, that's amazing in terms of the age of the universe, right? We're like 13.8 billion years old, and if we know very, very accurately what happened in the first 2 minutes, that's incredible. We still have that, but we're now starting to push it back to this 10 to the minus 32 of a second. And you know, that's where something called inflation probably happened. I could have given an entire talk on that because that's really fun. That invokes new physics. It seems ridiculous, and it was theoretically motivated, but it predicted the universe to be flat before it was measured. We've measured that, so that's a test of it. It predicted that the fluctuations of the CMB would have certain correlations on large scales. We've seen those. It also predicted that sort of, you know, families of initial fluctuations that would give rise to structure formation. We've also seen stuff consistent with that. And now we're looking at this one called gravitational waves, where we use the CMB to actually see the imprint of gravitational waves and potentially understand now 10 to the minus 32 of a second or something. And so I can't believe we're actually starting to ask questions legitimately, empirically, with measurements that are getting to those times. But going beyond that, I don't know. Absolutely. We have to learn how. So with any new tool, you always want to know what it is you're trying to build as you use the tool. And so I think the key is that, you know, there's a lot of enthusiasm to use AI and see how far it can go to help advance science. But I think we've got to make sure that the way we manage those initiatives is to accomplish scientific tasks rather than to use, you know, nebulously use AI to redo something. And so in my research, I'm starting to use it to design, you know, telescope parts. I'll just say it that way. It's camera parts. It's really fun, and it looks really promising. As a dyslexic, it has transformed my ability to write, because normally I would write a paragraph for 5 minutes and copy edit it for 45, and now I finish it in 6 minutes having AI copy edit it. So I think it really is a marvelous tool. But yeah, and I'm sure it'll be used. But at the end of the day, science is empirical, and what we're going to need is we're going to need to keep building. You know, we're building the instruments that are going to give the data sets that will do it. And with those data sets, AI can help. And I think for things like finding, you know, transients, so like sources that exploding stars, maybe, you know, funny things where black holes merge in our data, AI may be incredible at doing that very quickly, because it'll just spot a thing that's weird. But yeah, I don't know. It's going to be great. It's going to happen. I don't know what's going to happen. Yeah, I mean, Yeah, so the way, I've decided that I'm an experimentalist and that my job is to like build instruments that will, weigh in on as many of these things as possible. And so the thing I like about the Simons Observatory is that it's going to address the early universe. It's going to address structure formation. It's going to address all sorts of questions down to even, there's this really fun one where if you take planet or stars from the Gaia catalog and stack them in millimeter wave data, you can actually look for Oort clouds. So you could look for extrasolar Oort clouds. There's just all this stuff that'll do that's really fun. And I sort of view progress, the progress that I'm going to contribute to is making measurements, and then it may lead to one of these discoveries, but I don't know a priori where it's going to happen. Like if we find primordial gravitational waves, that'll be great. That may actually tell us how to unify all the forces. That's my dream. But if you just keep making better and more beautiful measurements, all of a sudden something won't fit, and you'll see something surprising. And I think the thing I lay it awake at night, I don't know, once in a while we'll daydream about is like, what if we find something weird? That's what I really want to happen. Thanks.
Very good. Yeah, thanks. Really good.